Okay, we are ready for section 5.5, which is going to be more about exponential functions, and just the same as we finish out chapter 5. All of these sections, as we kind of keep going, are just going to be some more sections to help you generate more functions that are represented by exponential equations. Okay, so we're just trying to put more tools in our toolbox essentially to come up with exponential functions to represent scenarios. The one big one that we've kind of hit on, but I want to hit on a little bit closer today, is section 5.5, which is about how exponential functions represent a constant percent change. So we've actually already seen this in section 5.1 when we were looking at that savings account balance. When we were looking at the savings account balance, we had that initial amount of $2,000, and it had that constant percent increase in the fact that interest rates are given in percentages. So if you remember back to this example, we ended with the function listed right here. And we got that function by saying, okay, we had to take 1 plus that interest rate, which was in decimal form, at 1 plus 0.035. We kept that original amount and kept adding that 3.5% interest rate to it. And that's exactly how growth factors are related to growth rates. So the growth factor is what you see in your equation. The growth factor here is a 1.035. The growth factor is always our A value of the equation. But kind of the interesting part is that that's not the same as the percent change, right? We took the percent change and added 1 to it to get to the growth factor. Our actual growth rate here was 0.035 as a decimal and 3.5% as a percentage. So those two things go hand in hand, but we don't necessarily see them exactly as they are. When we see the growth factor, we're not looking yet at the growth rate. We have to do a little bit of work to get there. They're not equivalent. We have to do that step of addition to get there. But they are always related in that exact same way. So every time to get to the growth factor, if we know that constant percent change, that growth rate, every time we will take 1 plus the growth rate to get to the growth factor. Just making sure that every time you're working with a percentage and you're doing math with a percentage, you want it in decimal form every time. Now, one thing I do want to note here, I'm going to do a little abbreviation to the side here, is the equation we have right now is the growth factor equals 1 plus the growth rate. Now, it will be helpful to kind of understand also how we get the growth rate from the growth factor. So if I was just given this equation up here from the beginning, and I wanted to take this equation and I didn't know that the interest rate was 3.5%, and I wanted to get that growth rate given the growth factor, then what happens is to solve for the growth rate in this equation here, just subtract 1 from both sides. So we can always get the growth rate out from the exponential function also by thinking, okay, that's just the growth factor I see in the function minus 1. So this is another helpful equation as well. Not just that the growth factor is 1 plus the growth rate if we're given the growth rate, but also that we can take that growth factor from the equation, just subtract that 1 to get back to the growth rate. So we're going to do this a little bit. We're going to just look at examples. How are these two things related? It seems fairly simple, but sometimes it can get a little bit confusing. So we're going to find the growth factor or the growth rate, whichever one's missing in the information. On A, we're looking at the fact that income is expected to grow at a rate of 2.9% per year. Okay, so income is expected to grow at, missing that word there, at a rate of 2.9% per year. We're looking at the growth rate then. That growth rate is as a percent, so we're looking at the growth rate of 2.9% there. Always to get to the growth factor, we want to think about that rate as a decimal. So that's 0.029 when we move the decimal place twice over or divide that percentage by 100. So then our growth factor, right, our math here is to always take 1 plus the growth rate of 0.029. So that equals 1.029. This is what we would put into our exponential function, but we state that rate always, right, as a percent. All right, see if you can do that next one then there. This one says that employment is expected to grow by 0.3% per year, okay? So if employment is expected to grow by 0.3% per year. Again, we see a percentage, so we're looking at the growth rate of 0.3%. Just make sure you do in fact change that to a decimal before you add 1 to it to get to the growth factor. So that is 0.003 as the decimal. Adding 1 to that, we get 1.003 as our growth factor. Okay, always take this percentage just as a reminder there. You're dividing it by 100 or moving that decimal place twice to get to the decimal form here. Okay. All right, now this last one is a good example of, okay, hey, here is the function of population growth. And from that function now, you could tell me how fast this population is growing in terms of percentage. You're given the 1.019 in the function, so it's your growth factor. And your growth rate is always 1 minus, sorry, nope, that's not right because we're going to end up with a decimal. Always take the growth factor minus 1, right? That's the function we came up with before. Your growth rate is your growth factor minus 1. I tried to just do that in reverse. So take your growth factor minus 1. That's the 0.019 you're seeing, which means that this population, moving that decimal back twice to convert it to a percent or multiplying by 100, is 1.9%. So the nice part here too is that given a function, we can report that growth rate. Okay. Now, it tends to be that growth rate and growth factor are kind of easy to see the relationship there. Whereas with decay rates and decay factors, the relationship between them is a little bit harder and a little bit less intuitive. So let's look at an example of how to get from the decay factor to the decay rate and vice versa. So back in 5.2, we had an example of decay. I'm going to take that caffeine example. So we came up with the function y equals 120 times 0.871 for our decay factor. So remember, the factor is what you always see in your function. Again, that's your a value. Even if with decay, it's still the a value. So we're seeing here that our decay factor is 0.871. But now, as we think about what that is not our decay rate. To get to our decay rate, we're going to have to do a little bit of work here. So our decay rate is actually, right, we're thinking about this as a percentage. In the function, we're keeping, if we think about 0.871, that's 87.1%. That's how much we're keeping of the 120. We're taking 120 times that percentage, and that's how much caffeine is remaining. So if we want to know how much decayed away, we have to think about that relationship of the decay factor with all of the caffeine, which would be 100% of the caffeine. So to get decay rate, we have to take 100% minus how much we were able to keep to get to the decay rate, which in this case would be 0.129. Taking that times 100 is 12.9%. So again, these don't even look like the same number, right? But they go hand in hand still. It's just that in our equation, we're always talking about the percentage we're keeping, but we talk about the decay rate as how much is actually going away. So we're losing 12.9%, but when we do that calculation, we want that percentage kept, which is the decay factor. So those are a little bit trickier. You don't really see the one sitting right there, right next to the growth rate, right? These almost look like two totally different numbers, but it's the fact that we're talking about remaining versus kept. Okay, so very important here, again, to get a formula to this so you always know what to do. So if you're finding your decay rate, we took 1 minus the decay factor there. And we know that this can go the other way around, right? So if decay rate equals 1 minus the decay factor, let's see if we can get an equation to also solve for decay factor. So if I want to solve this equation for decay factor, I could subtract 1 from both sides. That means decay rate minus 1 is the negative of the decay factor. So divide by -1 here, and something cool kind of happens here, which is that when we solve for decay factor, we end up with negative decay, whoops, see if I can get that to look a little better, decay rate minus 1, or plus 1, which is actually 1 minus decay rate is decay factor. So you'll notice that no matter what you do, whichever one you have, you'll just take 1 minus the one you have to get to the other one. Because the two together, right, it's true that decay rate plus decay factor equals 1. So no matter what, you'll just take 1 minus whichever one you have to get to the other one, because it's the remaining of that 100%. The hardest part here is just to realize which one you have. Do you have decay rate or do you have the decay factor? Always when you're doing that subtraction from 1 though, right, we're always thinking about both of these in decimal form to make that note for yourself. All right, so let's do some examples here to kind of sort through what's going on. So if we find the decay factor or the decay rate, which one are we given in A? It says sea ice is melting at a rate of 9% per decade. We see the percentage sign, so we know that we have here the decay rate. So the decay rate is 9%, always thinking about that as a decimal, that's 0.09. Always take 1 minus whatever you have to get to whatever you don't have, which in this case is the decay factor. So if I was trying to figure out how much sea ice was left, my decay factor that I would use in my function would be 0.91. But I would report that decay as a decaying at a rate of 9%. All right, B looks like we have a similar scenario because I see that percent sign. This time we have that a population is declining by 0.4% per year. Again, it's going away. This is a decay rate. So I see that percentage, and I know that percentage is 0.04%, sorry, 0.4%. That is a decimal. Convert that percentage to a decimal. That means you're dividing by 100. That's 0.004. Okay, always make sure you convert to decimal form. We have the decay rate. We'll take 1 minus the decay rate to get to the decay factor. So in my equation, right, my equation will be reporting that population every year. I get to keep 0.996 or 99.6% of that population, and that's the decay factor I would use in my function. Can you successfully go the other way around? So if you're given the function, so this is about the value of a car after so many years. Again, as we think about that function, this is the percentage of the value we're able to keep. It's in our function, so it's the factor, it's the A value. As we convert to decay rate, we still can take 1 minus the decay factor to get to the decay rate. So the decay rate as a decimal, always first, if you're using that decay factor, you'll get the decimal form, which is 0.11. That means that percentage is 11%. The value of the car is decaying by 11% per year. We get to keep 89% of it. Okay, hopefully you're starting to understand the difference there between the decay factor and the decay rate. I always see students struggle, and myself, more with understanding the difference between the decay factor and decay rate versus the growth factor and growth rate. Okay, but now that we have that tool, we can kind of think, okay, if I can find percent change then between an input and output variable, I can create functions now this way. I can create those exponential functions pretty easily, find that factor if I know the rate. So that's what we're going to do now. Okay, so we have tools to solve for these because we know how to find equations given 2 points. So you could find these equations I'm about to show you by doing what we did back in the previous sections, okay? But what we're gonna do today is think, okay, we have a new way of thinking about these exponential functions. Let's find them by thinking about the percent change, okay? So we're gonna look at each one of these, and the first thing we're gonna do is figure out percent change because we wanna use that to find then the factor and the exponential model, okay? So these are gonna be a little bit interesting, right? So here we have that a player's batting average dropped from 0.312 to 0.158 in one season. So this change happened in one season and we want to know the percent change. So anytime we find a percent change, we take the initial quantity. So we started at 0.312 was our batting average. And then we take that times some percent to get to the new quantity in the end. Okay, that's always what percent change is. The initial amount times whatever the percent change was, and that equals the new amount after the percent change. Okay, so we're going to now divide by 0.312 on both sides to figure out what that percent change is. So if you do that and divide, I believe this is a non-rounded number, but if it is, I rounded to 4 decimal places here. Okay, so that percent change I'm looking at is 0.5064. But we have to do a little bit of thinking here. This is going to be a decay. The batting average went down. And we know with decay, it's always a little bit harder to think about, okay, right now, am I looking at that decay factor or am I actually looking at that decay rate? Now, think about how exponential functions work. Y equals C times A to the X. Here, I have a very similar setup. My original amount, C, I'm taking it times something to get my new amount. So this that I'm looking at right here is more like my actual A value. So whenever we find percent change, we're actually finding that decay factor. So I wouldn't say here that my batting average dropped by 50.64%, because that's actually the percentage. When we found the percent change, we found the percent that we were able to keep of our batting average. We found the decay factor when we found this percent change. So when we actually report that percent change, we want to take the 1 minus the decay factor to find that rate we would actually report, 49.36, or sorry, let's go ahead and do decimal form first and then I'll convert that. That would be 0.4936 or 49.36%. So we would say the batting average went down, it decayed by 49.36%. But the way we do that with the math, right, is kind of the opposite of what you might think. It's what we kept here. So understand there that when you find percent change, you're finding actually the decay factor, and you have to do the work to find the decay rate. So this also helps us kind of understand decay rate a little bit better. So as we then now, as hopefully we understand the difference there between the decay rate and decay factor, we can put the exponential model together. So our output, our batting average is changing with seasons, right? This happened in one season, so that makes my input value number of seasons. And what's changing is my batting average. So now I can use this decay factor to set up my equation. Y equals the initial amount was 0.312. I'm going to take that times my decay factor, which is 0.5064 for every season that passes, if that is what continues to happen, if that percent change continues for this player. Okay, so again, decay always tends to be a little bit harder. So let's do another decay example here. We're going to relate this to a percent change of people getting the flu. Okay, kind of a good example of what's going on in the world right now too. So it says the number of people who got the flu last month was 55. This month it's 42. So the amount of people getting the flu each month is going down. We're seeing decay. So again, if we find that percent change, we think, okay, what is it now? What is it? The initial amount was that it was at 55. We take that times a percent to get to the new amount to figure out the percent change. We divide by 55 on both sides, and we see that that percent change that we come up with then, again, I'm going to do this to 4 decimal places to keep a lot of accuracy because we know we're working with factors here. and our exponential functions is about 0.7636. Again, that's the amount I kept. So I took 55 times 0.736. I kept 76% of this to get down to 42. So that percent change you're finding is actually hand in hand with the factor. That percent change is the decay factor that I'm looking at. That means I lost 1 minus 0.7636 or 0.2364, 23.64%. So I'm going down at a rate of 23.64%, but I always use kind of the opposite as far as with 100% the opposite of that when I'm talking about percent change. Okay, so I know that's a little confusing, right? It kind of challenges our brains a little bit because we want that p-value to be the decay rate, but it's not, it's the decay factor. Okay, so we use that decay factor to report the decay rate, but we go back to the decay factor when putting together the model. So the model here, if y is the number of people infected, right? If we want to know the number of people that are going to get the flu, then, and this is just in a month, right? So think about the numbers we're getting there. Those numbers are just how many people, more people get it each month, okay? X in this case is months surpassing, right? We went from 55 to 42 in a month. So X is just the number of months. Okay, then we end up here with Y equals, we started with 55 people getting it in a month. We took that times 0.7636 for each month, and that will report out then how many people get it each month. Okay, by the way that this problem was stated. All right, let's do a growth one. We know growth is a little bit easier to see the difference between growth and decay, but I'm gonna do an example here where maybe it's a little bit less easy to see, where you really gotta take those and make sure you use those equations we came up with, understand what's going on here. So this one says hourly wages grew from $1.65 per hour to $6 per hour in 30 years. So notice here too, when we find that percent change, it's going to be a 30-year percent change. So we started with a wage of 1.65. We take that times our percent change, a percentage, to get to $6 per hour. Now, when you divide each side by that original amount, always taking the end basically divided by the beginning to get that percent change, another way to think about it, that percent change we're looking at is 3.6364. Now, again, this is the actual number I took times my original amount. So still with growth, it's working the same way. The 30-year growth factor that I'm looking at is I took my original amount times that growth factor. So again, I'm not actually looking at the percent change here yet. I'm looking at a percentage, but not the percent that I want to report as my percent change. So to get from growth factor to growth rate, look up your formula, because this looks a little bit different, right? This is a number greater than 1. What are we looking at here? We still subtract 1 because that's our equation, right? We take, not decay, we take growth factors minus 1 to get to growth rates. That's our formula. So I'm still going to subtract 1. There's my growth factor right there. I subtract 1 from it, and I see that my growth rate as a decimal is 2.6364, and I always take decimal numbers times 100 to get to percent times 100%, and so I see that my percent growth here is 263.64%. And that's such a big percentage because we made such a giant leap here, right? From 1.65 to 6. That's my 30-year growth rate. It grew by 263.64% in 30 years. Okay, so if I'm setting up my equation, I go back to that growth factor. I report the growth rate if I'm talking about the growth in wages, but I use the growth factor in my equation. Y here is the wage, right? We're seeing how the wage changes over time, the hourly wage specifically, okay? And X here, if I use the growth factor as is, X is going to be 30-year time periods, right? Because that's what is happening. I did this growth in 30 years, so that makes X in terms of those 30-year time periods. So here we would have Y equals the original wage 1.65 times 3.6364 to the X if X is 30-year time periods. Now we know, right, from previous sections, how would this change if I said, okay, I want T to be the number of years? Can you guys do that fairly quickly now? You always take, you can leave the factor as is, and we say, okay, in order to convert, if I had the number of years, I would need to divide it by 30 to get to time periods. So my new time periods variable would just need to be divided by 30 every time. So this, again, a little bit more practice there on how to convert from one to the other. So if you took now this growth factor to the 1/30th power, you could see again the growth factor for years and get to the growth rate for how much that wage went up per year on average, again, during that 30-year time period. Okay, so big idea here is that we can now think about coming up with exponential functions by finding percent changes, or if given a percent change, we can find that function pretty easily. Okay, but interestingly enough, as we find percent changes, the math we do to find a percent change, we're actually getting that factor first, and we have to work a little bit then to get to that actual percent change. So understanding the difference between those factors and the percent changes. Okay, so the last thing for this section that I want to talk about is we know that constant amount changes, if you remember, constant amount changes are linear functions. Get that written down there. There we go. Constant amount changes are linear functions, and constant percent changes now are exponential functions. So yet another way to think about the difference between the two main functions we talked about in this particular class. So talking about constant amount versus constant percent, I have 4 examples here in the notes. So using that difference between constant amount and constant percent, can you come up with the function that models each one of these situations, okay? So they're either going to be changing by a constant amount and you need to come up with a linear function, or a constant percent and you need to use that to come up with the exponential function. So another good practice on giving those rates and coming up with the exponential function, and also knowing when, hey, this isn't actually a constant percent change, but I might be able to use some of my previous information from this class to come up with a function still that's linear. So on this first one here, we're looking at City A. It has a population of 60,000 in 1960, and each year since, the population has declined by 0.5% per year. Okay, so we're declining by a percentage. Right there, we can say, okay, this is exponential and it's exponential decay since it's going down. So I must have a function that's y equals c times a to the x, and I need to work to get c and a. I know the population in 1960. So let's make this nice and easy on ourselves and say, okay, let's let x be that reinitialized variable, years since 1960. That will mean that c is just 60,000 from the beginning, and we don't have to do that extra work to find c. Then, in years since 1960, the population is changing, so we're going to have y in this case be the population output, okay, after so many years. Now, this rate is per year, so I will have single years as my input variable. Okay? I don't have to worry about changing that from a certain time period, because that decay is giving to me in single years. Okay, so be careful here, you're given the decay rate, so we've got to use that, we've got to use that to find A. All right, so if we're going to find A, remember here the decay factor that we want to put into our equation is always 1 minus the decay rate. So here, if I'm finding the decay factor, I want to take 1 minus this decay rate, always in decimal form. Okay, put 0.5% in decimal form, that is 1 minus 0.005. The decay factor you're going to use in your equation is 0.995. So your final equation is y equals 60,000. It's continually multiplied by 0.995 to tell us how much population we have left every year, since our yearly decay rate is 0.5%. Okay, so how is this different than for city B that has a population of 200,000 in 1960, and each year since then the population has decreased, so it's still going down, but this time by 400 people every year. So this time is a constant amount change, right? This is a great example of the constant amount change. It's going down by 400 people every year. Okay, I see my iPad starting to lag here a little bit, so let me see if I can fix that. Okay, we're gonna see if that worked. So here we're changing by that constant amount. So can you put this into a linear function? It's that constant amount, so remind yourself here, we've got y equals mx plus b, different formula, right? Actually, in this case and throughout the whole thing, these are going to be my x and y variables the whole time, okay? So y is population and x is going to be years since 1960. So we're still looking at an initial amount here. For linear functions, initial amounts are b. So we're going to start out at 200,000 and we're going to go down by 400 people every year. X is every year, so y equals down 400 every year from that initial population. Difference between constant amount change and constant percent change there. Okay, so using those same x and y's, see if you can't set up an equation for city C and city D. Pause this if you need to. All right, so for city C, we're starting with 75,000 and it's going to increase by 1,000 each year. That's a constant amount, so we're looking at y equals mx plus b. Y equals 1,000 increase for every year, plus that original 75,000 from 1960. Did you get this last one here? This time we're going to start off with 80,000 and it's going to increase by 1.2%. Immediately that percent per year means we're looking at an exponential function. We know that C, right, C is the easier part here, is 80,000, but we got to stop and think about A. We have a growth rate here. So use your math, use your equations here. Your growth factor equals 1 plus your growth rate. Get that right formula in there. I have the growth rate at 0.12%, which is 0.012, dividing it by 100. That's 1.012. This is my growth factor. So that's the A value I'm going to use here. So y equals that original amount. I'm going to add in that 1.2% each year, and that's every year. So x can be in terms of years, and I have my exponential growth function using that given growth rate. Okay, so work on the homework. I'm going to test you a lot in the homework about whether or not you can give me the factor versus the rate and a bunch of different scenarios. So hopefully by the time you're done with that, you'll feel confident in the difference between these two things. All right, again, always reach out to me if you have questions, okay?